Alright, so we finished up with the RIP, pretty much. RIP's not a very good protocol. I would probably never use RIP in the real world, even though we use it all the time in class. Uh, we're now going to put everything back the way it was, pretty much the way it was. I'll leave this uh, connection there for the two switches. I'll bring the serial back up. And then we're going to configure Ospf. Yeah. No shutdown. Then we will do a no router RIP. And turn off RIP. We will turn on Ospf, router Ospf. We need to put process ID. And then we put our network command, network. This is the syntax for turning on Ospf. That network statement uses what Cisco calls a wildcard mask. Essentially, it's like the opposite of the net mask. You can think of these 255s or these ones as the don't care bits. So essentially, I'm saying I want to enable Ospf on any interface that has a 192.168 IP address because I don't care about these last two octets. So Ospf does have this idea called areas. So we're just going to be using one area, so everything will be in area 0 for our configuration. So essentially I've enabled Ospf on every interface since everything is using 192.168 area 0. So I will go do that on the other routers now. I don't want to RIP, I want to know what to RIP. Oh, incomplete command. Thank you, router. So there we go. Now my routers are configured for Ospf. You see these messages getting printed to the console table. Process number 1, neighbor, gives you IP address and the interface, loading to full. With Ospf, with RIP, we didn't really form any relationships with those routers. We would send routing updates to a multicast address, and all other routers would look at that multicast address and listen for that multicast address and then get the updates. With Ospf, we form neighbor relationships with neighbors we're connected to, and there are a bunch of different requirements for why we will form a neighbor relationship, and some things will prevent us from forming a neighbor relationship when we should. So if you got things to work in RIP okay, and then when you switched over to Ospf, you couldn't get routes to work a certain way and from a certain neighbor, check your net masks, because one of the things that has to match is the net mask on the interface has to be the same. So we're supposed to have a bunch of /30s on our router interfaces. It would still work if you had a /30 on one of them and a /24 on the other one. Using RIP, it would still work. However, with Ospf, they would not agree to become neighbors because they don't have the same subnet. So in this case, I'm pretty awesome, so I'm pretty sure I configured everything right. So let's look at my routing table. And I have a routing table with some routes learned through Ospf. A couple things to notice. O for Ospf tells us how we got our route. Why is it interesting to have these in the routing table? Well, you can be using multiple routing protocols at once. You could be sharing routes with one group of routers using OSPF, and you'd be sharing routes with another group of routers using RIP or something like that. If we look at our routing table, we actually have an entry for 11.0/27, 11.252/30. If we compare that to RIP, with RIP, before we disabled auto summary, we just had one route for 11.0/24. OSPF does not summarize routes, so there's no need for the no auto summary with OSPF. So what route is our packet taking? Well, let's go look at our bottom router over here. OSPF uses cost as its metric, so the link type is considered in deciding which route to take. So considering that fast Ethernet is faster than serial, our serial link, I would hope that it's going across our fast Ethernet links. So from this LAN to get to 22.0, it's going to go out to 11.253, going out faster than at 0.1. So it's going to go across our fast link. It's going to go up here and then across this way and then back down. In theory, in class, we're actually going to have gig across the top. So in class, it should go across the gig. But since we're only pretending this is a gig, it's not really gig, there's no telling what it's going to say. And it may have both routes in there again. So let's look at the routing table. Show IPO, IP. So we're trying to get to 22.0. Yeah, we have two equal cost routes in this case. Both of them have a 3 for the cost. So that's kind of what I expect to happen. So in the class, we're going to do some throughput tests, and you should get a faster speed before the failure, perhaps. It should also recover more quickly from a failure. So we have a ping running. Let me go get my stopwatch. I'm not actually going to get my stopwatch yet. Start my ping again because I want to. What we need to do is we need to take down both these links to force the traffic to go across the serial. So I'm going to kill both these links, then start my stopwatch, and then bring up the command prompt with the ping to see if it's going across the serial and how long it takes it to figure out that there's a problem. And then stopwatch. Oh, I killed the stopwatch. Oh well. Right now on my recording time, we're at like 7:45. So I'll tell you what the time is based on that. Where's my ping? All right, so we dropped a few pings so far. It's been about 15 seconds. Look at our routing table. See if it has anything interesting in it. It doesn't. All right, it's back. Probably about 30 seconds with OSPF. So that was a lot faster than 7 minutes for stability. So EIGRP, a Cisco proprietary routing protocol, can only be used between Cisco routers. We don't really talk about it in this class. However, it has some enhanced features where it pretty much predetermines the next best route at all times. So you have the route you're using, and you've already figured out what route you're going to use if there's a failure. So EIGRP converges very, very quickly. So if you're ever in the real world and you're only using Cisco equipment, I'd probably recommend using EIGRP. So let's see what else we're supposed to talk about. That was really about it for the lab part. Yeah, about it.